Hi everyone, welcome to this M2D2 meeting. Today we have Zhening with us, who is a student at MIT CCEL, and who will be presenting his work on predictive chemistry augmented with test retrieval. Thank you so much, Zhening, for coming here with us today to present your work. And looking forward to it.
Thank you. Okay, so I guess I will begin now. Everyone can hear me, I suppose, right? Awesome. So hello everyone, I'm Zhening, and today I'll be presenting predictive chemistry augmented with text retrieval. This work was done at MIT CSIL and the MIT Chemie department in collaboration with Yuji Chen, Dr. Yuji Chen, Zheng Kai-tu, Connor Coley, as well as Regina Barzilai, Professor Regina Barzilai. So in machine learning for predictive chemistry, the task is formulated as follows. We begin with a structured database of labeled data. And such databases include, for example, PubChem or Reaxys. And these databases include many labeled pairs of data corresponding to reactions and various output labels. And we use this data to train a machine learning model to perform a predictive chemistry task. And such tasks can include, for example, molecular property prediction, and that involves predicting various properties of a molecule, for example, the ground state energy or antibiotic properties. It can also include reaction outcome prediction, where we want to predict the result of a particular chemical reaction, as well as retrosynthesis planning, where we want to design a certain molecule, such as a drug molecule, and we want to plan out the synthesis pathway. And these predictive chemistry models can then be used to accelerate and enhance drug discovery processes. The question that we're trying to tackle here is the issue of the fact that obtaining this structured database, the labeled training data for the machine learning model, is not a very easy process, because the data that we have in its original form is given in the form of journal articles as well as patents in the form of unstructured text. So obtaining this labeled data in a structured format suitable for machine learning model training requires information extraction from the unstructured text. And there are many ways to do this information extraction. For example, No 2012 has an entire PhD thesis on this, and that work uses specific models, specific tools that are tailored towards the chemistry literature to extract the data. And that is a very costly and expensive process. There's also been recent work that uses deep learning models to do information extraction, but this also faces various challenges, such as the lack of training data, the fact that for different predictive chemistry tasks, we want different sorts of labeled training data. So we need task-specific information extraction models for these different tasks. And finally, these systems all are prone to error. So we propose an alternative where we directly use a lot of this unstructured text and augment our model with these unstructured texts. And one thing to keep in mind here is that we're not completely replacing the labeled data with the text paragraphs. Instead, we have a certain amount of labeled data, but it's limited, whereas we have an abundance of the unstructured text. So we augment our model with this large abundance of a text corpus. So what might this look like? Well, let's take as an example this task of having as input a reaction and predicting the reaction conditions that are most suitable for that reaction. So we see that in the simple case where we do not have text retrieval, in the case where we just have a traditional machine learning model, the model takes the input and tries to predict the output. So that's quite simple. Well, the model architecture itself may be very complicated, but this is the way this problem is set up in that situation. When we additionally have an unlabeled text corpus, then the model can take the input and retrieve text paragraphs that it deems to be related to the input. For example, when we have this reaction here, then it can try to find text paragraphs that either describe the reaction or describe similar reactions. And the model can then take this extra information as extra input to enhance its predictions. And this is particularly helpful for reaction condition recommendation because similar reactions or reactions of the similar reaction class often use the same reaction conditions. And in this case, in this example shown here, we can actually see that for this input reaction, similar reactions actually use the exact same reaction conditions. So the model in this case can simply read off the corresponding reaction conditions and output those. So more concretely, our model architecture, TextReact, involves two components, the text augmented predictor and the smiles to text retriever. So the text augmented predictor takes as input the original chemistry input, as well as any text that can be retrieved from the text corpus, and it tries to predict the output label. On the other hand, the smiles to text retriever does the job of retrieving the related text paragraphs. So it looks at this input reaction and the big reaction text corpus, and it aims to find the text paragraphs that are closest to the input reaction within the embedding space. And these are called the nearest neighbors. And these nearest neighbors are then given to the text augmented predictor to make the predictions. So now I'm just going to go a bit in more detail for the two components of the model architecture. The smiles to text retriever consists of the chemistry encoder as well as a text encoder. So the text encoder takes a paragraph of text and embeds it into an embedding TI. The chemistry encoder takes as input some chemistry, which could be a reaction or a molecule in the form of a smile string. Here, the smile string is just a standardized way of writing a molecule or reaction in a string format. The chemistry encoder encodes the smile string into an embedding XI as well. And the way we train the smiles to text retriever is to align the chemistry embedding space and the text embedding space, so that if we have a text paragraph that directly describes a certain reaction, then we want the corresponding embeddings to be close within the embedding space. And this training is accomplished through contrastive learning. So as a recap, we have XI being the result of encoding a chemistry input, and TI is the result of encoding a text input. And we define the similarity between the two embeddings to simply be the inner product between the two embedding vectors. And contrastive training loss looks like this. The negative sum over all data of the logarithm of this expression over here. Trying to minimize this loss encourages increasing the similarity between corresponding chemistry and text paragraphs relative to the distance between or the similarity between the chemistry input and all other text paragraphs. So minimizing this loss will align the chemistry and text embedding spaces such that if we have a chemistry input in a text paragraph that describes that chemistry input or describes something similar, then the two corresponding embedding vectors will be close within the embedding space. So in TextReact, we in particular choose to initialize the text encoder with a pre-trained Cybert checkpoint. So Cyburst is a transformer encoder that has been pre-trained on scientific text. And since all of our text paragraphs are from chemistry journal articles or patents, this will give the text encoder head start in our fine-tuning, in our contrastive learning fine-tuning. The chemistry encoder is pre-trained Camberta, which is a encoder transformer, a transformer encoder that has been pre-trained on smiled strings. So now let's take a look at the text augmented predictor. The text augmented predictor takes as input the smile string, the original input to our problem, as well as retrieved texts that have been outputted by our retrieval model. The transformer encoder then encodes this input, including the smiles and the retrieved text, into an embedding vector, and this is then decoded into the desired output. The loss function used here is simply the maximum likelihood objective. We want to maximize the probability that our model assigns to the training data set. Note here that even though we have text paragraphs that directly describe every single reaction input, when we train the model, we use the retrieved text paragraphs because in actual deployment, we do not know the text corresponding to user input, but instead have to retrieve them. We also incorporate an auxiliary masked language modeling loss. And so we mask some tokens in our input, and we add a prediction head on top of the transformer, on top of the last layer of the transformer, that predicts the probability distribution over tokens, aiming to reconstruct the masked tokens. So the MLM loss here is just the reconstruction loss, where we try to maximize the probability that we assign to the correct or ground truth masked tokens. Masked language modeling has been very popular in the pre-training of transformer encoders and semi-supervised learning in general. And in our case, we employ this to encourage the learning of a better encoding of the inputs and to have the transformer better learn the relationships among different parts of the input, so that during actual prediction, this will decrease the risk of the transformer relying too much on a particular source of the input, such as a particular text or the chemistry input. So yeah, these are the descriptions of the model architecture and the problem so far, and I will take any questions. Sorry, the light just turned off. Let's see. Is this a question in the chat? Oh, yes. So here's a question from Prudentio. Do you do any normalization for the embeddings to avoid that longer text have more match during the alignment? Okay, so what we do, so I assume this is referring to the contrastive learning part of the retrieval model. Is that correct?
Yes.
Yeah, so all of the inputs are embedded to a vector of the same length. So even for longer text, it will also be embedded to an encoding that is of a fixed vector length. In that case, we do not normalize our vectors, but we did actually take a look at the resultant embeddings, and we found that they all have essentially the same magnitude. I think the number that I remember off the top of my head was between 2,000 and 3,000. Like all of the embeddings for both the text as well as the chemistry was the same magnitude. So this also empirically verified that a normalization was not necessary in this case, and simply taking the inner product was sufficient as a measure of similarity. Yeah. Okay, another question. Pre-processing pipeline for the text extracted from published articles. Okay, I think I'll be mentioning this, but I also won't go into much detail. I think I'll answer this question at the very end. Okay, so yeah, let's continue with the talk. Slide is not advancing. Okay, good. Cool. So the model that we proposed is a general framework for text retrieval augmented to chemistry prediction. However, we will consider two specific tasks to test our model. One I have already mentioned before, which is reaction condition recommendation. As a recap, we take as input a reaction that does not have the condition specified, only the reactants and the products. And the model aims to predict what are the most suitable reaction conditions. And this includes the catalyst, solvent, and the reagent for the reaction. And the other task is one-step retrosynthesis. And this is retrosynthesis referring to finding the reactants or the synthesis pipeline for creating desired molecule. And one step here refers to the fact that we're only considering one step in the process. So the input will be just the target product molecule that we're trying to synthesize. And the output label is going to be the reactant or the reactants that will produce the product. For retrosynthesis, we consider two different kinds of models. One is to directly predict the SMILE string of the reactant or the reactants. And this is called a template-free model. The other approach involves first predicting the reaction template of the reaction. And the reaction template can be roughly understood as the class that the reaction belongs to. And this will be chosen from a finite list of reaction templates that are extracted from the training data set beforehand. And after we predict the reaction template, we obtain the desired reactants by simply using existing chemistry software to apply the reaction template in reverse to the product molecule. And this approach is called a template-based approach. So for the training data, we will have two kinds of training data. One is labeled data, where we have inputs and their corresponding ground truth labels for our respective chemistry prediction tasks. And the other kind of data is going to be the unlabeled text corpus. So the labeled data we will take data compiled by Lowe 2012 in his PhD thesis, compiled from the US Patent Trade Office, also known as USPTO. And then for the retrosynthesis task, we will take the USPTO 50K dataset from Coley et al. 2017. And this is a brief summary of the order of magnitude of the sizes of our data sets. So for USPTO, for RCR, reaction condition recommendation, we have about 600 to 700,000 labeled data pairs. And for the USPTO 50K, we have about, 50K data points as indicated by the name of the data set. We will be considering two different kinds of data splits. One is the more standard random split, abbreviated as RS over here. And the random split is exactly what the name suggests. We randomly split the entire data set into train, validation, and test sets with a ratio of 8 to 1 to 1. And the other data set split is the time-based split. And this is less standard, but it has been used quite a few times in the past in the field of machine learning for chemistry prediction. For the time-based split, the way we split the data set is to split it based off of patent year. What does this mean? It means that we take a particular year or 2 years in the past, and we take all the data that has been published before these 1 or 2 years to be part of the training data set. And then we take these 1 or 2 years to be the validation set, and everything published after to be the test set. And the idea behind such a data split is that it kind of simulates a real world situation where we train our model on all the existing training data, but at deployment, the user input that we get is from a future date. And we expect a data split in the time-based way of splitting data to be more challenging for the model, because oftentimes patents or journal articles published in a similar paper or a similar time frame or in the same paper are often related to each other and are therefore more similar. Whereas those published in a future date will look a little more different from those that are from the past. Our unlabeled text corpus is from the US Patent Trade Office, and this has been compiled by Lowe 2012. So now I'm answering the question in the chat about the unlabeled text corpus. So the details I'm not very familiar with. I will refer the audience to the Lowe 2012 PhD thesis. They have compiled a lot of data from the published patents and organized them into many, many paragraphs, about 4 times as many paragraphs as there are of labeled training data for RC, 2.9 million. And every paragraph averages about 190 tokens. And this token count is based off of the default tokenizer that we are using for our model, which is the Cybert tokenizer. Each paragraph describes a particular reaction, and most of these paragraphs can be matched with the labeled data. So in that case, we filtered all of our labeled data to include only those that have been successfully matched with a text paragraph from the text corpus. And as a result, our labeled training data, instead of just input alpha pairs xi and yi, for each such pair, we also have the corresponding text paragraph describing that reaction. So we have many triplets among the training data set for the labeled training data. And in addition, we have a lot more unlabeled text paragraphs for which we don't have labeled training data. And so when we train our retrieval model, we look at every single possible input reaction, and we take its ground truth, or also called gold text, as a positive sample for the contrastive learning. And all the pairs between the chemistry input and all the other text paragraphs is going to be treated as negative samples for our retrieval model. And this includes all pairs between this input chemistry as well as the entire unlabeled text corpus. So as a recap, the positive sample, the similarity goes into the top of the numerator and the loss. Everything else goes into the bottom. And minimizing the loss will allow us to align the chemistry and the text embedding spaces so that we will expect similar vectors to be semantically similar. And then for the training of the text augmented predictor, we have an input as well as text retrieved using the retrieval model, the nearest neighbors, and we concatenate them and we try to predict the output. So in deployment, the retrieved text will be the top 3 texts, top 3 nearest neighbors, for example, within the embedding space. For training, we can make use of the fact that we know the ground truth text paragraph corresponding to every input. So with probability 1 minus alpha, we simply take this gold text as well as the top k minus 1 neighbors that are retrieved. Here, little k is taken to be 3. So we have 3 texts augmented to the input. However, although this represents the situation where the user inputs a reaction that has been studied before, as a result of which we actually have the retrieved text. In many cases in the future, the user may input a reaction for which we do not have the goal text. And instead, we can only find maybe some text paragraphs that describe reactions that are similar to the input reaction. So we simulate this during the training stage through a random sampling strategy, where with probability alpha, we take the top big K nearest neighbors, where big K is a larger number, such as 10, and we randomly sample a smaller number among them, where little k is 3. So we take the top 10 nearest neighbors and randomly sample 3 of them. And this simulates the situation in deployment where we do not necessarily have very good text that can be retrieved and only have somewhat similar text that describe the reaction. Okay, so this slide summarizes our results. We compared TextReact with Transformer, here representing a chemistry-only model. When I say chemistry-only, I mean that there has not been text retrieval, and the model can only base its prediction off of the chemistry input. So Transformer is basically the minimally different model from our TextReact that does not use text retrieval. And we can see that all of these green bars, which are TextReact, are a lot higher, especially for RCR, than the blue bars, which are the transformer baseline. So especially for RCR, we can see that text retrieval boosts the top one prediction accuracy by a lot, from about 30% to 90% in the random split, and from 20% to 80% in the time split. And we can see smaller but still appreciable performance increases in retrosynthesis. This table shows a little bit more detail. Transformer is what I mentioned before, the minimally different model from TextReact that does not use text retrieval. Camberta is a variant of Transformer where instead of using the Cybert pre-training checkpoint, we use the Camberta pre-training checkpoint. And we see that using having pre-training on smiles in Camberta does not actually boost the baseline by a lot. And we still have a significant performance boost from TextReact using text retrieval. One thing to note is that Transformer and Camberta happen to be the state of the art of reaction condition recommendation models that do not use text retrieval. Because of this, I will not be showing the baselines that have been previously published because they all have worse performance than the transformer model. However, I would like to bring some attention to the reaction fingerprint baseline, because here we're comparing Gautel 2018, which was the first reaction condition recommendation model using deep learning, as well as reaction fingerprint retrieval, which is a pure retrieval model. The pure retrieval model, what it does is it takes the difference in Morgan fingerprints between the product and the reactant, and it uses these embeddings and takes the nearest neighbors of the input reaction within this fingerprint embedding space. And it simply outputs the reaction conditions of those nearest neighbors. So it does not try to do any inference. It simply just outputs the reaction conditions of the nearest neighbors. And we notice that just by doing that, we already outperform this previous deep learning baseline that actually tries to predict the reaction conditions using just the inputs, using a neural network. And this gives us more confidence that retrieval is very helpful for the reaction condition recommendation task. So We also tested our model on a more stringent setting. This setting we will call gold removed corpus. In this setting, for every input, after we retrieve the text, we remove the gold text. And this is to simulate a situation where the user provides a reaction that has not been published before or that simply is not described by any text paragraph in our text corpus. And so in this more difficult setting, we actually still see an improvement relative to the transformer baseline. Of course, we see a decrease in performance from when we do have the gold text, thus telling us that the model is indeed looking at the text paragraphs to make its predictions. However, the fact that we can still see an improvement from the baseline where there is no text retrieval shows that the model is able to get information from text paragraphs that describe reactions similar to the input reaction to make predictions. An even harder test setting, which is denoted by the red bars here, and is called the time split corpus, is where instead of having access to the entire corpus, we only have access to the corpus from the date corresponding to the training set. So the part of the corpus that describes patents or journal articles published in the date range corresponding to the test set is completely removed. And in this case, we can see that the performance drops further to approximately the baseline performance. And what this tells us is that as new publications become available, including these into our text corpus, will allow the model to gain more information from these texts, the retrieved texts, and thus boost its performance. So finally, we conducted some ablation analysis to test the different components of our model. So smiles only here refers to the transformer baseline I was referring to before. And we have already shown that it is significantly outperformed by the TextReact model on RCR, and also outperformed to a decent extent by retrosynthesis on retrosynthesis. Full and GR here refer to the testing setting of retrieving from the full corpus and retrieving from the gold removed corpus. GR stands for gold removed. Text only is opposite to the smiles only model, where we do not provide the model with the original chemistry input smiles, but instead it only has access to the retrieved text. And interestingly, we find that the performance in RCR remains very high despite a slight decrease in performance, showing the importance of text retrieval for RCR, whereas for retrosynthesis, the performance decreased a lot. And then if you recall from what I mentioned before, we also incorporate an auxiliary masked language modeling objective. So removing this objective gives a decrease in performance, especially for retrosynthesis, thus showing that it was essential to increasing the performance of our model. It allowed the model to better learn the relationships between different parts of the input to integrate the text as well as the chemistry input to make its predictions. And then we have the no pre-training model, where we do not start with the Cybert pre-train checkpoint to train our model and then fine-tune it on our data, but instead we just start to train from scratch. And this results in a decrease in performance, showing the utility of having a pre-trained model to begin with. And then finally, one thing I would like to mention is that past literature on text retrieval has proposed an alternative approach to integrating text and input, where you take the different retrieved text separately. And for each separate retrieved text, we combine it with the original input and make predictions. And then we then aggregate the predictions made by each text at the very end. So we call this separate neighbors. So we also tried out this approach and we observed a decrease in performance here. Further analysis showed that the model, when it was able to look at the entire input sequence at once, including both the original input and all the retrieved nearest neighbors together, when the transformer has access to the entire input sequence as such, it is actually able to obtain information from what the distribution of the nearest neighbors looks like. So when it can see that the nearest neighbors look very different from each other, then it will know to put more emphasis on the actual nearest neighbor, the top nearest neighbor, which is expected to describe the reaction much better than the other ones. Whereas if the retrieved texts all look very similar to the text augmented predictor, then it will know to apply a more equal weight to the information in the separate nearest neighbors. So encoding everything together has been able to boost the performance of the model. Recall that I also mentioned the random sampling strategy where during training with the probability alpha, we actually incorporate random sampling from the retrieved nearest neighbors, where we take, for example, the top 10 nearest neighbors and randomly sample 3 of them. And so the analysis here shows the effect of the random sampling ratio on the performance of the model. We can see that there's a trade-off, and the optimal point of the alpha random sampling ratio depends on whether we're testing using the full corpus setting or using the gold removed setting. And this makes intuitive sense because in the full corpus setting, it is often the case that within the test set, when we give the model an input, it is able to retrieve the gold text. So if we incorporate the gold text in a higher number of training data inputs, then the model will perform better. On the other hand, for the gold removed setting, we can see that it prefers a larger random sampling ratio alpha. And this also makes sense because in the gold remove test setting, we remove the gold text from the retrieved nearest neighbors. And so a higher performance is achieved when we simulate this during the training process, where the random sampling strategy only samples not the top nearest neighbors, but the top 3 out of, for example, the 10 nearest neighbors. And oftentimes this will no longer include the gold text, and this simulates the situation where we are unable to actually find a gold text given a user input.
So for the RCR and the retrosync, is this for the transformers or the for the pre-train only?
For the what only, sir?
For the pre-train only.
Oh, so the pre-training is the way we initialize our model. Like
Okay.
before we, so our entire training process is more of a fine-tuning process based off of existing pre-training checkpoints. So our text augmented predictor, instead of training our entire model from scratch, our text augmented predictor is initialized with the Cybert pre-trained checkpoint. And instead of training our entire retrieval model from scratch, the two components of the retrieval model are initialized with pre-trained checkpoints, the Cybert checkpoint and the converter checkpoint. If that makes sense.
Yeah, this makes sense. Thanks.
Yeah, no problem. Okay, so yeah, so to conclude, we have proposed this model called TextReact, which uses text retrieval to augment predictive chemistry models. We have tested our model on 2 specific predictive chemistry tasks, including reaction condition recommendation and one-step retrosynthesis. And we see a huge performance increase due to text retrieval for reaction condition recommendation, and a decent performance increase as well on one-step retrosynthesis. And our results verify the utility of using text retrieval and text augmentation as an approach when we have limited labeled training data while we have an abundance of unlabeled text. And this is particularly applicable to chemistry and drug discovery because this is a field where new findings are published as these unstructured text formats in patents and papers. And so when these new findings become available, instead of extracting labeled data from the new findings and retraining our model, which is very expensive, we can instead directly incorporate the unstructured text into our text corpus, which already gives a performance boost of the model compared to without any text retrieval. And so that's all I have for you today. Again, my name is Zhening Li, and our paper, you can check it out. It has been presented at the EMNLP conference in 2023. This is our code base. And thanks a lot to all of my co-authors, especially Dr. Yuji Chen, who is the leader of this project. And thank you all for coming today, and I'm happy to take any questions. Suppose I can start with the questions that have been asked in the chat first. Okay. Let's see. Time split be subject to data leakage. Do you perform any measure to avoid it, like measuring similarity? I suppose you're referring to the fact that let me just go to the corresponding slide here. Random split, time split. Yes, so you are correct that for the blue and green bars, our text corpus will include potentially text paragraphs that already correctly describe the text inputs. However, I wouldn't consider this to be data leakage because in real usage of the model, user input will often actually be reactions that have already been published in the literature and therefore included in the text corpus. And it will often be the case that we do indeed are able to retrieve the text paragraph describing the reaction. But your concern is valid. So we do also test on the situation where we remove the goal text from the input to the model, and the results are presented here. We still get a performance boost. Indeed, if we are extremely tough on the model and remove all of the text corpus corresponding to the period of the test data set, then we don't see an improvement compared to the baseline. But the fact that we see this performance decrease, I think, actually shows the utility of using text retrieval. Because when comparing the yellow bar and the red bar here, the difference is that with the yellow bar, we have more retrieved text that simulates the real deployment setting, where when more findings become available, we can actually incorporate these new findings into our text corpus very easily. Whereas for labeled data, it is much more difficult because that involves retraining the entire model. Okay. Next question here. Formulation mechanism of negative samples on slide 14. Okay, let's take a look at that. Yes, so negative samples, positive samples. So as a recap, our data can be considered to be having two parts to it. One part of the data set is the labeled data, where we actually have we actually know for every single input, for every single input reaction, we actually know the text paragraph that directly describes that reaction. So that is the positive sample. And everything else is considered negative sample. So this includes all the other text paragraphs within the labeled training set, because all of these text paragraphs do not directly describe the input reaction. And for the unlabeled text corpus, for the entire unlabeled text corpus, we simply do not know whether any of these text paragraphs directly describe the input reaction. So because of the fact that most of them will definitely not, we simply take all of these to be negative samples. So all pairs involving this input reaction and a text paragraph from the unlabeled corpus is considered a negative sample. And so, yeah, that is the formulation of the positive and negative samples in our contrastive learning loss here. So the positive sample goes into the numerator, and both the positive and the negative samples all go in the denominator. And then minimizing the loss will encourage the alignment of the chemistry and text embedding spaces. Okay. Someone asked, is the template-based approach a classifier, or does the language model output the smarts of the template? Yes. So the template-based approach is based off of a previous template-based model called local retro. So the way we do this is, I don't really have slides for this, but I can hopefully describe in words clearly enough for you to understand. So we have this transformer. The transformer encoder is kept, but we do not use this decoder. So we do not actually predict the smart string of the reaction template. Instead, what we do is that at the top layer of the transformer, we have embeddings corresponding to every single input token. And we tokenize the smile strings in a way such that every token corresponds to an atom or a symbol representing the structural relationships between atoms. And we construct atom embeddings from the corresponding tokens at the top layer of the transformer. And then we construct bond embeddings by concatenating two atom embeddings. And on top of this, we put a linear prediction head so that we predict at every single atom whether or not we apply a template to the atom, and if we do, what template we apply to it. And for every single bond embedding, which is a concatenation of two atoms, we predict whether or not we apply a bond template to that bond, and what bond template to apply to it if we do apply a template. And then after this, we get a probability distribution over all templates and also locations to apply the templates. And we take the template and the location of applying it to the one with the highest probability. So that is our template-based model. It is essentially the same as local retro. Next question. Do you have any generalization result with holdout reaction classes? So unfortunately, we did not do such an analysis. Yeah, we did not do such an analysis, but I think it would be really nice to see more clearly generalization out of across reaction classes. So one generalization result that we do have is from the time split setting. It is more of a time-based generalization. It tests how well our model trained on past data can generalize to future reactions, which might look very different. So in the graphs that we've seen, yeah, RS represents the random split. and TS represents the time split, which to some degree assesses the model's ability to generalize. And we can see that our performance remains strong under the time split. Yes, so someone asked, could not for most reactions, multiple reaction conditions be correct? That is indeed the case. We consider a reaction condition to be correct if it is present among the set of reaction conditions that is correct, if I remember correctly. So for every single data point, the ground truth is actually a set of possible reaction conditions that be correct. And we consider our model output to be correct if our model output is among the set of reaction conditions that be correct. Here, when I say reaction condition, it does not refer to one single reagent or one single solvent. It refers to the entire set of reagents, solvents, and catalysts. So for this comparison, we still do exact match. So if the entire set of reactants, reagents, solvents is present among the ground truth set of reaction conditions, which are themselves sets of reagents, solvents, and catalysts, then we consider our model output to be correct. Yes, so temperature and pressure have been studied in reaction condition recommendation models. For us, we did not incorporate temperature and pressure. We considered reagents, solvents, catalysts. But we imagine that we can also apply our approach to incorporate temperature and pressure as well. In this case, the accuracy in the past, I believe, has been the distance or the square distance to the ground truth. For reaction conditions, most of the reactions have multiple reagents. What do you count as correct? Oh, yes, I believe I have answered this question already. So, yeah, a label is going to contain a set of reagents, solvents, and catalysts. And our model predicts a set of reagents, solvents, and catalysts. And if the entire set matches exactly the ground truth set, then we consider that to be correct. Okay, last question is, do you have reactions where there is no reagent condition reported in your data sets? Yes, if there is a reaction where there is no reaction condition, then it is excluded from our data. So we only train on data that actually have labels. Cool. Are there any questions that would like to be asked live? I can address them very quickly now as well.
What was the compute that you used for
Yes.
performing the? Yeah.
Yes. So this depended on the task. For reaction condition recommendation, we used 8 GPUs at once. It was
Okay.
either A6000 or A100 most of the time.
The 80
And
gigs ones?
what's that, sorry?
The 80 gigs ones? The
Yeah, 8
or the
GPUs. Yeah,
the
for
VRAM. I'm specifically asking about the VRAM. How much VRAM did you use? The 40 gigs one or the 80 gigs?
yes, 40. The 40
Okay.
40 gigabytes. Yeah.
Okay.
And then we use 8 of those at the same time, simultaneously run for my memory is a bit fuzzy. I believe it was 1 or 2 days. I believe about 1 day was enough. It could have been 2 days.
Okay.
For retrosynthesis, it was shorter. We used the same amount of GPUs and VRAM, but it ran faster. I think it ran within a day.
Okay.
Yeah, so that is what the compute looks like. And I believe more details can be found in our paper.
Yeah.
Yeah,
Thanks.
no problem.
I have
Cool.
a last speculative question, maybe.
Yes.
So you do retrieval currently by, I'm assuming, some kind of similarity on the
That's
embeddings,
correct.
and the embeddings are
Yes.
just like, pre-trained with alignment. Do you think there'd be utility to kind of learning to query more explicitly?
Learning to query as opposed to using an existing algorithm,
Well, as
such
opposed to
as,
just training with this sorry, the word is escaping me, but contractive learning, right?
yeah,
Um,
right. So yeah, so currently the way we do it, we have this dual encoder. We encode text and chemistry input, and then retrieval involves doing a maximum inner product search for which there are existing
yeah.
algorithms. Yeah, as to learning to retrieve, um, I'm unfamiliar with existing literature on something of this sort. Um, I personally would imagine it would be quite expensive to have to maybe have a deep learning model that computes the similarity for every single text paragraph, the text corpus, because there's a whole lot of them. There's like 3 million of them.
Yeah.
But that does sound like a cool idea. I'm not aware of people having attempted it. Maybe you know more about this than I do.